Hi everyone, welcome back to the time series forecasting playlist. This is the fourth video. So in this particular video, we'll focus on the concepts that are absolutely critical if you want to move from theory to practical forecasting. We'll cover the ideas that will directly impact models' performance and decision making. So without wasting any time, let's get started. So these are the list of terminologies that we will cover in this video. And if you might have watched the previous videos, there will be some terms that you might have already heard of, but we will again revisit them. So let's start with the most basic question. What exactly is time series? Time series is simply data collected over time where time order matters. So if you look at this particular plot, you can see that we have data points recorded over time. So this is called a time series. For example, we can consider time series as daily stock prices, monthly sales, temperature values, yearly GDP, and so on. So anytime you hear time series, think of it like some variable measured repeatedly with a time attached to it or over time. Now that brings us to the next term, which is the frequency. So you need to ask this question to yourself is that how often is the data recorded? It could be recorded at a daily level, which we call as daily frequency. It could be at monthly frequency. It could be at hourly frequency. So you need to figure that out, like what frequency of time series data you have or what frequency you want to deal with. Many time series models assume a fixed frequency. So before modeling or before starting with any kind of modeling process, ask yourself this question: what is the frequency of my time series? Now let's understand a very closely related concept to frequency, which is granularity. So you need to ask another question, is that how granular you want your data to be or how granular your data is. Let's say, for example, you have a data recorded every second. Maybe it's like some kind of a sensor which records a particular data point every second. But in your case, you might not need that level of granularity. Maybe you need the data at a hourly level or maybe at a minute level. So you need to think about your problem statement and what granularity you need to deal with. So one more example could be that in my particular case, I had to deal with some time series where it was too granular, like it was at a daily level and the values were too low. So it becomes very difficult to forecast such time series because there might not be too much patterns in it. So we had to roll it up to a monthly level to get some information that we could model. Now we have covered the three concepts. Now let's jump on to the fourth concept, which is the univariate versus multivariate time series data. So this is a very important concept. So univariate refers to a scenario where you just have one variable changing over time. For example, monthly sales. So in that case, you try to predict the future of the same variable using its past values. But in a multivariate time series, you might have multiple variables changing over time, which could provide some information to each other. They could be influencing each other. And a very good example for that is weather data. In weather data, we have the temperatures connected with humidity, connected with precipitation, connected with wind speed. So all these variables kind of influence each other. So in that case, you would want to model that forecast using a multivariate forecasting strategy. Let's keep it simple. Univariate is where you predict the future of same variable using its past values, but in multivariate you have multiple variables changing over time and you use their past values to model it. The next concept is trend. So we have already discussed about trend. Trend is the long term direction of the data of the series. So in this case, if you look at the time series, what is the long term direction of the series? If we visualize it, we could see that it is in a upward trend. So in this case, we have a upward trend. For example, we have growing revenue, increasing population. But in this case, if you look at a particular horizon from here to here, you can see that there is a downward trend. So there is a local trend in the data where we have a downward pattern. Therefore, there comes a very important term called as global trend versus local trend. And we need to identify both in our forecasting strategies. So we need to see how the local trends affect the forecasting, and if we really need to change our extrapolation or change our prediction as per the local trend, or keep it aligned with the global trend. So in this case, if you see, we have local trend, local downward trend in the data. So we need, whenever we need to extrapolate from this point onwards, we need to consider both this particular local trend as well as the global trend in the data. And a trend does not have to be linear in every case. It can be curved, it can be exponential, that we need to identify. So it can be a linear trend, it can be a curved trend, it can be an exponential trend. So we have covered the trend. Then comes the seasonality factor. And seasonality, as we have discussed, is a repeating pattern over time. So in simple terms, seasonality is a pattern that repeats at a fixed interval. And the key phrase is fixed and predictable repetition. For example, the sales of ice creams goes up every summer. That is kind of fixed. Electricity demand spikes up during summers, or maybe like a retail sales increases in the festive season. So we have Diwali festival. So there will be an increase in sales of some product during that time period, and it kind of repeats every year. Or maybe Christmas effect, or maybe you might have heard Black Friday sales. You might have heard the festival sales, and so on. So these are kind of seasonal effects. It repeats at the same interval. And there's another component called as cyclic component. And this is where people generally get confused. Cyclic patterns look a lot like seasonality, but without a fixed period. So, for example, economic booms or recessions or a long business cycle. And the major difference is that it does not have a fixed length, unlike seasonality. So, it can last up to years in some cases, and it can occur at an irregular timing. So the basic difference is that seasonality has a fixed pattern and cyclic component has a variable length. And then the third very important component is noise or residuals. So after we remove the trend, the seasonality, the cyclic components, and any exogenous effects, what remains is called as noise. So we have covered seasonality, we have covered cyclic component, now we are at noise. So let's say we have a time series, which is in this pattern. Now let's say we remove the trend component from this. It will look something like this. Now let's say we remove the seasonality component from it. It might look something like this. Now this is what is called as noise. And this is the part which has no pattern in it. It is completely unpredictable, and it represents the randomness or unexplained variation. So when you are doing time series forecasting, in your case, if your residuals have some patterns, that means your forecast is not good. There are some patterns remaining in the residuals that your model missed out on. Let's say in a scenario where you have created a model for time series forecast, and you have, let's say, an accuracy of, let's say, 70%, but in your residuals there is no pattern remaining. It is plain and simple noise. That means you have done a good job, and that is the best you can do for that data. So you have tried to capture all the meaningful pattern from it. So the point to keep in mind is, if your residuals still show some patterns, your model is definitely missing something. Now let's look at few versions of noise. So we have like white noise, we have red noise, and we have a random walk. Now let's try to understand them in detail. So what is white noise? White noise is pure randomness. And the main characteristics of a white noise is that the mean is zero. So in this case, if you see, the mean is zero. And the variance is almost constant. So if you see, the variance is kind of constant. There are some spikes here and there, but almost all the data points have a constant variance. And there is no correlation between time steps. In simple words, yesterday tells you nothing about today, which kind of violates the basic assumption of time series forecasting, that time series data should be autocorrelated. And generally, people say that white noise is often the ideal residual, what you want after modeling. So if your residuals look like white noise, your model is a good model. Now let's look at red noise. Red noise is kind of opposite of white noise. Here, the values are correlated over time. So your red noise might not be stationary. It will not be stationary because there will be some shocks here and there. There will be changes happening. So for example, let's consider climate variables or long-term environmental process. So in red noise, as it is correlated, yesterday still affects today, but it shares some of the components from the white noise, which is zero mean. So basically, red noise is randomness, but with some memory, which is again difficult to forecast. And the third version of noise is random walk. A random walk is a special kind of process where each value depends on the previous value plus some random noise. So mathematically, random walk is today equal to yesterday plus random change. And the classic example is stock prices. And the key properties of random walk is there is no fixed mean, variance increases over time. So if you see, the variance is completely different for these two horizons, and it is impossible to predict long-term direction. It could move or it could drift away in any direction. Now let's consider backtesting. What exactly is backtesting? Backtesting is like a term for testing, but because we are working with time series data, we behave in such a way that we are in the past and let's now see how the model performs. So we are going back in time and testing it. Suppose you have a data from here to here. You are at this point. So what you do is you go back in time and split your data into two parts. And the first part is train and this part is test. And you train your model on the training data and then test it out in this region. This is called as backtesting. And one thing to make sure is that time order matters. Now let's look at what are exogenous variables. Let's say we have a sales of a product and we have 2 years of information. This is the first year and this is the second year. And if you see, in this case, we have a spike at the end of the year. And these are Black Friday effects. So these are external variables that are affecting your sales. So these are called as exogenous variables. Any external factor that influences the time series but cannot be predicted by the model itself are called as external effects. In here we do see some seasonality, but let's say you had a promotion in the second year and you see this spike. Now there is no seasonality to this spike. So this is something that you already have information because you have ran the promotion. So you can feed this information as an additional variable to the model. And the classic examples of exogenous variables are holidays, promotions, weather changes, policy changes, competitors' data, and so on. And another concept that we have already covered is stationary and non-stationary time series. And I have a separate video. You can go in the playlist and watch it. I'll just mention a few of the points that we need to keep in mind is that for a stationary time series, mean is constant, variance is constant, and the correlation structure doesn't change over time. So if you see in this case, all those 3 points make sense. So in short, the statistical behavior stays the same. And most classical time series models assume stationarity. But in case of non-stationary time series, the mean is changing. So if you look at this horizon, the mean is changing. The variance changes. If you see, the variance is changing and the patterns kind of evolve. That's the core difference between stationary and non-stationary time series. And before we model a non-stationary time series, we need to make it stationary. Because, as I mentioned earlier, most classical models assume stationarity. And some of the ways to do that is differencing or transformation or decomposition. Differencing is nothing but subtracting the previous day value with the current day values. We call that first order differencing. We can also have second order differencing when we do it twice. So we have Dickey-Fuller test to check the stationarity of the data. So what we do is we do the first order differencing, check if the data is stationary or not. If not, then we do a second order differencing and so on. These are some of the high level concepts that we will deal with in the upcoming tutorials. But for now, this is the core difference between stationarity and non-stationary time series. Now let's look at another very important concept. It's a very important statistical term which is called as Gaussian distribution, and it is like a normal bell-shaped curve. And why is it important in time series? Because many models assume that errors are Gaussian. You will become familiar with a term called as confidence interval in the future. So confidence interval depends on the Gaussian distribution of a time series, and all the other statistical tests rely on it. But one thing to keep in mind is that we don't need the data itself to be Gaussian, but residuals behaving Gaussian is a good sign. So finally, we have covered all the concepts in detail. So final thoughts on this is that time series forecasting is not about just throwing models at the data. It's more important to understand the data generating process, and it's very important to get familiar with these concepts that we have discussed. So that finally brings us to the end of this fourth video in our time series forecasting playlist. At this point, I believe you should have a much clearer intuition about how time series data works and why understanding the data, the structure of the data, is just as important as choosing the right model. In the upcoming videos, we will take this understanding further and start connecting these concepts to actual forecasting techniques and how we take the decision to model it. So if you found this video useful, don't forget to like and subscribe and share it with anyone who's trying to learn forecasting or data science. Thanks for watching. I'll see you in the next video. Thank you.